Hello, this will be our third installment on section 4.2. Today I'm going to talk to you about the problems that come in the latter part of the homework where we pick up the applications of Rolle's theorem or the applications of the mean value theorem. All of these application problems deal with roots. The finding of roots, we know we can do that with the intermediate value theorem in an excessive amount of work, or we could cheat, use our TI-89 of course, but the mean value theorem and Rolle's theorem, the corollary to the mean value theorem, they allow us to find out how many roots a function has. So what I'm going to do is I'm just going to talk through a couple of the problems. Now I did an example in class. I believe I did problem 18. Problem 17 and problem 19 are very similar to that problem. The theme on every one of these problems is going to be if I'm supposed to show that something does occur, I'm first going to assume that the opposite occurs. And I'm going to try to show that if I make that assumption, that assumption will lead me to a contradiction. And that contradiction, therefore, would mean that my initial assumption must be false. So every one of these problems, until we get down to problems 23, 24, 25, those problems are all going to focus on us first assuming that what they tell us is true is actually false. All right, it's kind of a fun logic exercise. So if we take a look here at problem 19, 19 says, show that the equation x cubed minus 15x plus c equals 0 has at most one real root in the interval -2 to 2. So that's problem 19. So if you're following along at home, look at problem 19. And remember, you can pause the video and then start back up anytime you want. Now, problem 19, the first thing we have to do is say to ourselves, does this satisfy the condition of Rolle's theorem? Rolle's theorem, remember, demands that the function be continuous on the closed interval, -2 to 2 in this case, and differentiable on the open interval, -2 to 2. Well, problem 19 deals with x cubed minus 15x plus c. That function is a polynomial, so because of that, we have a theorem that says polynomials are continuous everywhere on their domain, so we know that polynomial is continuous everywhere, meaning from -infinity to infinity. So it's clearly continuous on a closed interval from -2 to 2. Going beyond that, if we take the derivative of x cubed minus 15x plus c, we get 3x squared minus 15, another polynomial. That polynomial is defined on all real numbers. Therefore, the derivative exists everywhere. Well, if the derivative exists everywhere, then by the definition of differentiability, the function is differentiable everywhere. And we can extend that, therefore, to say if it's differentiable everywhere, it's clearly differentiable on the open interval from -2 to 2. So we have the first two conditions of Rolle's theorem met. Now we're supposed to show, according to this problem, 19, there is at most one real root in that interval. So let's assume there are two real roots between -2 and 2. Well, if we have two real roots, this is going to begin to look a lot like problem 18. If we have two real roots, that means we have two x-intercepts, i.e. we have two places, say a and b, where the functional value of a equals the functional value of b because they're both 0. They're on the x-axis. Well, what does that mean? Well, hopefully we can come to some kind of a statement that says, well, that doesn't make sense. So we look at the derivative. The derivative, remember, is 3x squared minus 15. Now, we have said that Rolle's theorem applies. So the derivative has to equal 0 between a and b, someplace between a and b, because that's what Rolle's theorem says. If f of a equals f of b, the derivative equals 0 between a and b. So if we look at our derivative, 3x squared minus 15, now that has to equal 0 between a and b. Well, does it? We can check. 3x squared minus 15 equals 0 becomes 3x squared equals 15. Now, What do we know about 3x squared minus 15 on the interval from -2 to 2? See, that's the key idea. That's the question that we have to ponder to answer problem 19. What do you know about 3x squared minus 15 between -2 and 2? Because Rolle's theorem guarantees there has to be a place between -2 and 2 where that function equals 0. Well, if you take a look at that parabola, 3x squared minus 15, that parabola opens up. But does it ever equal 0 between -2 and 2? If you put -2 into 3x squared minus 15, that's 3 times 4, 12, minus 15. That's -3. So at -2, our parabola is below the x-axis. What about +2? Well, +2, we get 3x squared minus 15. That's 3 times 4 minus 15. That's -3 as well. So at +2, our parabola is still below the x-axis. So we've reached a contradiction. Rolle's theorem says that the derivative has to equal 0 between a and b. And we know we have some roots, 2 of them. We made that assumption. A and b, somewhere on that interval, -2 to 2, we've assumed that those roots exist. But unfortunately, all the values between -2 and 2, when we plug them into the derivative, they're all negative. They're all less than 0. But Rolle's theorem says that the derivative has to be 0 someplace between -2 and 2. Well, there's our contradiction. So we have to go back and we have to look at what we assumed to get ourselves this far. We did not assume the function was continuous because it is continuous. It's a polynomial. We did not assume that the derivative was differentiable. Sorry, the function was differentiable because we proved, because the derivative exists everywhere, we proved the function is differentiable. The only assumption we made was that there were 2 roots, a and b, and therefore there aren't 2 roots between -2 and 2. So every one of these problems, up till we get to problem 23, 24, they all work the same way. Assume what you want to happen doesn't, and see if you can reach a contradiction. All right, I'm going to put another video up here just in a sec, and that one's going to be about the problems at the end of the homework assignment, 23, 24, 25, 26. All right, have a great day. I hope this helps.